Okay, now let's get into matrix multiplication. The multiplication of two matrices. And to do that, I'd like to just remind us of our original system. We'll talk about a multiplication of a matrix with a vector. A vector is really just a special kind of matrix. It's a m by 1 matrix, for example. But the process is the same. So let's look at our first equation that we looked at before. Again, it was coefficients multiplied by n unknowns. And likewise, we could look. So this is equation 1. And I'd like you to start being a little more comfortable with using these variables. So this is we would express equation I as ai1 times x1 plus ai2 times x2 all the way out to the ai n times xn is equal to the ci. So that's the ith equation, where the first, what I've drawn here is the first equation, and this is the ith equation. And so we can describe this multiplication as the product of a vector containing all the a matrix containing all the a's with a vector of x's being equal to a vector of c. And we can write that multiplication as the sum as k goes from 1 to n of ai, again for the ith equation, for the kth unknown, and you see that we're summing from k goes from 1 to n, and that gives that's equal to the ith constant. So this is a formal definition of how we carry out this product. So let's look at a relatively simple system in which we have a matrix, say 2, 0, 5, and 1, 3, 2. For 1 minus 1. So this is our A matrix, and we're multiplying it by vector x, and we'll just say it's 5 minus 2 and 1. Not giving myself enough room here. And that is equal to, again, we're multiplying each of our unknowns here by each of these coefficients. So you can think of it as multiplying this row, again, row 1, by, of course, this vector, which is just a column, right, by this column. So we'll multiply this row down this column for the first element of the C matrix, right? And that's just 10 plus 0 plus 5. And that gives C1, which is 15. Plus 5, right, it's 15. To get the second element of C, we have to multiply the second row of our matrix times our vector. So we're going across and down again, and we have 5 minus 6 and 2, and that's equal to 1. And then finally, for our third element of our product vector, we multiply the third row down this column again, and we have 20 minus 2 minus 1, and that's equal to 17. So that's an example of a 3 by 3 matrix multiplied by a 3 by 1 vector, and the result is a 3 by 1 vector. Now let's look at the product of two matrices that have more than one dimension. So let's look at A times B is equal to C, and we would write, so that the product of A times B is equal to, again, we're going to sum over, for k equals 1 to n unknowns, but this time we're going to describe we're multiplying the ith row of A, right, times the jth column of B. And that will give us our product matrix, the ijth element of C. So again, this is the jth column of B times the ith row of A. And that's how we multiply two matrices that aren't vectors. And as an example, I think I can fit it all on one page here. Let's look at 2, 0, minus 5. Actually, well, let's start with our 2, 0, minus 5, 1, 3, 2. I'm sorry. Let's just use our original matrix right here. 2, 0, 5, 1, 3, 2, 4, 1, minus 1. That was our original matrix. And we'll just use our original vector that we had above here for the first row of our matrix B, but then we'll just add another column. And so the answer, we still get 15, 1, 17 for the first row, okay, of our product. But now we have to multiply each row of A by the second column to get the second column of our product vector. So we have 2 plus 0 plus 5 will give 7. And we have 1 times 1 is 1, 3 times 3 is 9, plus 2 times 1 is 12. And then for the last element, we have 4 times 1 plus 3 minus 1 is 6. So that's how we carry out a multiplication of a 3 by 3 matrix with a 3 by 2 matrix. And the result is a 3 by 2 matrix, a matrix with 3 rows and 2 columns. And let me just make this perfectly clear. For example, if we have for row 2, again, we multiplied row 2 across. We took row 2 across and multiplied it down column 2 to get the element 2, 2, or C2, 2, just to make that clear. And the other example I'd like to show is if we had a 2 by 2 matrix, a 1, 5, and a 1, 2, we could multiply that by a 2 by 3 matrix, for example, and we would get 1 times 3 plus 2 times 5 is 13. The first row times the second column is 2 plus 5 is 7 to get the second column in the first row of the product matrix. And then 1 times 1 plus 0 gives 1 for the third column of the first row. And then when we have 1 times 3 is 3, 2 times 2 is 4, is 7. And then we have 2 plus 2 is 4. And then 1 plus 0 is 1. And this was an example of a 2 by 2 times a 2 by 3 times, and that gives a 2 by 3 matrix. And you should notice here that in each of these cases, in each of these cases, the dimensions, the inner dimensions, when we put our two matrices together, are the same. So the requirement is that the inner dimensions match. And the other thing you notice is that you should notice that the outer dimensions, when we multiply two matrices, are the outer dimensions of the product. So the outer dimensions give the dimensions or form, sorry about my messy handwriting, the form of the product. Okay, so you can always check to see if it's possible to multiply two matrices by checking when you put the two matrices together, the two inner dimensions must match. And you always know that the product matrices has the same dimensions as the outer two matrices. So two matrices are conformal for multiplication if the number of columns of the first matrix equals the number of rows of the second. So that's the requirement of two matrices in order for them to be conformal for multiplication. As an example, if we had a matrix that was, say 10 by 3, and we tried to multiply it by matrix B, which was, say, 4 by 2, then we cannot do this. These two matrices are not conformable for multiplication. However, if we had our 10 by 3 matrix and we multiplied it by a 3 by 4 matrix, then that would give a matrix. Again, the two inner dimensions are the same, and that can be done, and the resulting matrix would be 10 by 4. And likewise, when we multiplied our matrix times our vector, we had, for example, a 3 by 3 matrix multiplied by a matrix which was 3 by 1. It's also called a vector if it has only one dimension. Then that gave another vector, which I'll denote as lowercase c with a single bar, and of course that was 3 by 1. Okay, so it's following the same rules. And because of this rule of conformality, you should notice that matrix multiplication is in general not commutative. Unlike normal multiplication of numbers, you can't reverse the order in general of two matrices when we do this, and those two can be equivalent. So an example is if A is m by n, in order for it to be multiplied by another matrix, in order for that operation to be defined, B must be n by some other number, and I shouldn't use m, I should use L, for example, and that will give, no, I better use m, I'm sorry, I better use m here. And that gives an m by m matrix C. Whereas if we reverse the order of the matrix multiplication, we would again have an n by n matrix being B, n by m, that's what B was, multiplied by an m by n matrix, which was A, and that would give a matrix C, which in this case was n by n. And you can see that these two matrices are not equivalent. They're of different sizes, they're of different forms. Okay, so again, it's in general not appropriate to say that the, well, in general, it means that the order of the multiplication does matter for matrices.